Hello SpaceX, my name is John Marshall. I'm a junior in computer engineering and I'm applying for your spring 2016 co-op position. I'd like to take this opportunity to share with you one of the cool creative projects I've been involved with at Virginia Tech for the past few semesters, and that is Virginia Tech's Project Ellie. Project Ellie is a high-altitude balloon project, and my contributions have been to the hardware and software design of the flight computer, which also collects data from the instruments.
Here's a look at our design schematic done in Eagle. We built our flight computer based off of last year's design and added more scientific instruments. The text in green is what was added by myself and the team. I was responsible for the humidity sensor, the Geiger counter, and the GPS unit. This photo shows the flight computer without peripherals. The main components were the SD card, the orientation sensor, a temperature and pressure sensor, and the Atmega 328. Not shown in this photo is the GPS, Geiger counter, and the humidity sensor, and those are the three peripherals that I worked the most on. I liked working with the Geiger counter the most because out of all the other peripherals, it was the hardest to test and the hardest to work on since it was a high voltage component and presented a shock hazard. In this picture, I'm testing the Geiger counter with an alpha radiation source. We use this because alpha radiation does not penetrate things, and it's not harmful unless you were to eat it. The Geiger counter communicates with the Atmega 328 via an interrupt line. So all it does is it sends a pulse down that line and it interrupts the Atmega from whatever it's doing. And then the Atmega then goes into a section of code that increments a counter by 1. So every time that the Geiger counts, that variable gets updated and stored to an SD card. The other cool thing about the Geiger counter was being able to figure out how it works. The capacitors act like tiny buckets. They're filled up in parallel, then connected in series to create a higher voltage. A high voltage is necessary for a strong electric field. When a radioactive particle enters the strong electric field, it acts almost like a small short, which is what makes the ticking sound when the Geiger counter detects radiation. That tick is then sent as the signal to the Atmega. This is the humidity and temperature sensor. It uses a widely known communication standard called I2C. It was also fun to work with, mainly for testing purposes. In order to test it, I breathed on it because I knew that my breath had to be more humid than the air indoors, and sure enough, when it was working, after breathing on it, it registered higher humidity. So this is a view of the inside of the payload package. All of the wires are color-coded. The Arduino was used for servo control. It controlled 2 cut-down servos. One was for cutting off the balloon, and another was for the parachute in case the payload got stuck in a tree. I wrote the code for that as well, but it was very simple code because it was just calling 2 functions that were timed. The balloon would be cut down only after a few hours, and then an hour after that, the payload would be cut down, giving it plenty of time to reach its target altitude and also enough time on the other servo to parachute back to Earth. The payload also contained the batteries, flight computer, and 2 cameras. One camera was inset into the lid though and isn't shown in this picture. The transmitter had a nullifier on the end of it to stop it from being damaged in the event that it was turned on but not yet connected to the antenna. This photo was taken shortly after launch, and it's a really good photo because it shows all the different pieces of the high-altitude balloon project coming together. There's a separate team that worked on the antenna, a separate team that worked on the parachute and disconnect, and another 2 people that researched a lot about the balloon because there was 2 different types of balloons that we could have chosen to go with, depending on how long we wanted the payload to stay up there. The team I work with concentrated mostly on the payload. Our balloon reached an altitude of 118,000 feet, which is higher than the 110,000 we were shooting for, so we're all happy about that. Unfortunately though, for us, when the balloon came back down, it might have been hit by a strong gust of wind because once it reached 20,000 feet, we were unable to track it on amateur radio, and inevitably lost our payload. That being said, though, I'm still very happy about the role I played in making Project Ellie happen, and I also learned invaluable experience such as what it's like to work on a project which relies heavily on teamwork, where each member has to accomplish their work for that aspect of the mission, because if one part fails, the entire mission could fail. Also, the project had many constraints, such as power budget, a weight allowance, a strict deadline, and the amount of data we could store since we were taking high-resolution imagery on 2 cameras, as well as a huge amount of flight data. There were many trade-offs and some disagreements, but in the end, we were able to make the mission a reality. This final picture was taken by the Ellie mission that launched a year prior to ours, and I think it's awesome because not only can you clearly see the curvature of the Earth, but there's also the blackness of space mixing with the beautiful blue of the atmosphere. Having worked with the team where we shared the thrill in getting a payload to 118,000 feet, I'm extremely excited for the chance to be a part of SpaceX, where I know the sky isn't the limit and where I'll be a small part of helping with the mission to get people to Mars. Thank you for listening, and thank you for the opportunity to apply.